Usually, when you open up a highly technical proposal about, the future of artificial intelligence or exascale cloud computing, you kind of brace yourself for this pure engineering speak.
Right, the really dry stuff.
Exactly. You expect bandwidth projections, power consumption metrics, maybe uh, a deeply dry analysis of silicon fabrication yields.
Thermal dissipation charts, all of that.
Yeah, you expect it to be cold, binary, and completely grounded in the physical reality of the semiconductor industry. But the source material for today's deep dive opens with a sentence that completely derails that expectation.
It really does. It's quite the hook.
The very first line of this incredibly dense, forward-looking tech proposal reads, quote, "The impending age of abundance was prophesied in the scriptures thousands of years ago."
Which is just a massive, jarring tonal shift, right?
Yeah.
It immediately signals to you that we are not dealing with a standard Silicon Valley pitch deck here.
No, definitely not.
I mean, the author is attempting to bridge ancient eschatology and futuristic orbital mechanics in literally the exact same breath.
And honestly, that is the lens we have to use for this entire deep dive. We are looking at a post from April 11th, 2026, from the blog Netizen. It's written by Paramendra Kumar Bhagat,
Right.
and the title is "The Orbital Compute Revolution: Why Low Earth Orbit Holds the Key to Our AI Future." But, you can't just read that headline and dismiss it as another space tech thought experiment.
No, you really can't. That context is vital for the listener, because when you look at the bibliography listed in the margins of his blog, it paints a picture of a deeply systemic, almost aggressively holistic thinker.
Yeah, I mean, you see titles in there like Calciism, the economic and spiritual blueprint for an age of abundance.
Sitting right next to highly technical market analyses like agentic AI set to explode in 2026.
It's wild. And then there are these deeply philosophical, almost theological works, right? Like Prophecies Are Proof of God, mixed in with blueprints for reorganizing the United Nations.
And treatises on precision genetics.
Yeah.
It reads like the reading list of someone trying to architect an entirely new civilization from scratch.
I'm bothered by normal boundaries.
Completely unbothered. He doesn't care about the traditional lines between engineering, economics, and spirituality.
The mention of Calciism is particularly fascinating, I think, because in Hindu eschatology, Kalki is the final avatar of Vishnu.
Right, the one prophesied to appear at the end of the current Dark Age.
Yeah, the Kali Yuga. He's supposed to usher in this new epoch of truth and abundance, and the author is explicitly mapping that ancient theological concept of an age of abundance onto the very real impending arrival of artificial general intelligence.
And infinite compute. He's looking at server racks not in isolation, but as the physical engines of that prophesied abundance.
Which is just a staggering way to look at a data center.
It is. He connects human history, macroeconomics, and hard physics, searching for this ultimate synthesis. He's basically arguing that the current trajectory of the tech industry is fundamentally at odds with the physical reality of our planet.
And that brings us to the core thesis of his post, right? The rapidly exploding demand for artificial intelligence simply cannot be sustained on the surface of the Earth.
Period. He argues we have to take the cloud, which, right now is just millions of tons of concrete and silicon sitting in places like Virginia or Iceland,
Right.
and move it into actual orbit, low Earth orbit.
But before we start throwing server racks into rockets, we have to deeply understand the problem on the ground. Because the author makes an incredibly aggressive point right up front about the sheer scale of compute demand.
He doesn't just say it's growing.
No, he says it is devouring infrastructure. Like, we are moving way past AI models that just generate text or images.
We're talking about agentic AI operating continuously.
Exactly. Real-time analytics across global finance, autonomous systems managing entire city grids, highly personalized genomic medicine. The parameter counts of these models are just scaling exponentially.
And the training runs are requiring hundreds of thousands of next-generation GPUs running simultaneously for months at a time. To grasp the gravity of this, you really have to look at his critique of the current tech industry's physical strategy.
Which he calls an outdated mindset, right?
Yeah. He describes this mindset where companies just keep buying racks of servers, pouring concrete from massive ground facilities, and crossing their fingers that the local utility companies can somehow keep up.
Which they can't.
No.
Yeah.
He is highlighting a profound mismatch between the infinite, boundless potential of software and the strictly finite, immutable laws of terrestrial physics.
You're trying to run a technology designed to simulate reality on a planet with strict thermodynamic and spatial limits.
Exactly.
I was trying to visualize this terrestrial trap for the listener. It's kind of like a biological organism that has evolved to grow indefinitely, right? But it's trapped inside a terrarium.
Oh, that's a great analogy.
At first, it just takes up a little more space. Then it starts consuming the nutrients faster than they can be replenished. And eventually, it starts altering the ambient temperature of the terrarium itself.
It cooks itself.
Right. No matter how efficiently you optimize the organism's metabolism, it is going to hit the glass. You cannot code your way out of thermodynamics.
You really can't. And those physical glass walls are already causing massive friction in the market. The text points out 3 specific, insurmountable bottlenecks, starting with the electrical grid.
Let's talk about the grid. Yeah.
The electricity consumption of these hyperscale data centers is already straining national power infrastructures.
Yeah.
When we talk about exascale computing,
Which is systems capable of a quintillion calculations per second.
yeah, the energy draw isn't measured in megawatts anymore. It's measured in gigawatts.
Yeah.
You are essentially taking the baseload power requirement of a mid-sized industrial city and plugging it into a grid architecture that was fundamentally designed in the mid-20th century.
For like suburban sprawl and light manufacturing.
Exactly.
Okay, let me play devil's advocate here, though. Why are we acting like the grid is permanently frozen? I mean, we've built massive infrastructure before. We industrialized the entire planet. Why not just aggressively build next-generation nuclear power plants right next to these data centers?
Or carpet entire states in advanced solar, right?
Yeah. Why is that not the answer?
Well, we certainly possess the engineering capability to build next-generation nuclear, like small modular reactors. But the author's point hinges entirely on the timeline mismatch.
Ah, the speed of it.
Yes. The physics of building a nuclear plant involves a decade of regulatory approvals, environmental impact studies, site prep, and construction. The grid inertia is massive.
It moves at a glacial pace.
Even large-scale renewable deployments require massive new high-voltage transmission lines, and those face immense local opposition and permitting delays. Conversely, AI compute demand is doubling in a matter of months.
A hyperscaler needs a new gigawatt facility online by 2028, not 2038.
Right. The software is evolving at the speed of thought, while the power infrastructure is evolving at the speed of concrete and bureaucracy.
So the organism is outgrowing the terrarium faster than we can build a bigger glass box. And even if you solve the power generation, you immediately hit the second wall the author identifies, which is thermodynamics. The text points out that cooling requirements are enormous and environmentally costly.
This is perhaps the most intractable terrestrial bottleneck. A high-performance GPU running at full tilt is essentially a highly sophisticated space heater.
Just blasting heat.
Exactly. It converts electricity into complex mathematics, sure, but also massive amounts of thermal energy. If you do not actively, aggressively remove that heat, the silicon physically degrades and melts down.
And on Earth, our primary mechanism for moving that heat at a massive scale is water.
Right. You rely on evaporative cooling towers. Hyperscale data centers pump millions of gallons of clean, drinkable water through their systems to keep the silicon from cooking itself.
Which is insane when you think about it. We are talking about regions where aquifers are already depleting, and we are boiling millions of gallons of fresh water into the atmosphere so an AI can, optimize a supply chain or generate a video.
The environmental optics of that, let alone the physical reality of water scarcity, make it completely unsustainable.
And if you attempt to pivot away from water to, say, closed-loop air cooling,
the energy penalty is staggering. You end up using massive amounts of electricity just to run the fans and compressors to chill the air, which further exacerbates the first bottleneck, the grid strain.
Right, you're back to square one.
Furthermore, you are still dumping gigawatts of thermal energy directly into the local environment, creating these massive urban heat islands.
Which feeds directly into the third terrestrial limit the author explicitly names: land. He notes that land is incredibly scarce in the areas where talent and demand are most heavily concentrated.
Network topology dictates that you want your data centers relatively close to where the data is actually being generated and consumed.
For latency reasons.
Exactly. If you are serving the financial sector in Manhattan or the tech sector in Silicon Valley, you want your compute facilities nearby to minimize the physical distance the data has to travel.
But those exact regions have the most expensive, highly contested, and densely populated real estate on the planet.
You cannot invoke eminent domain to bulldoze 20 city blocks in London to build a 1 million square foot server farm. It's just not going to happen.
So the hyperscalers are pushed out into the deserts or remote rural areas where land is cheap. But out there, the power grid is weakest and the water is scarcest.
It's a perfect vicious cycle of terrestrial constraints.
It really is. If the power grid is tapped out, the water supply is evaporating, and we've run out of viable land, we have essentially boxed ourselves in on a planetary level, which leaves us looking at the only environment where thermodynamics actually works in our favor.
And the author uses a very specific framing for this transition. He calls it an inversion.
An inversion.
Yeah, he argues that the harsh vacuum environment of space actually takes every single one of Earth's physical bottlenecks and flips it into a structural advantage.
Okay, so if Earth is the cramped studio apartment, space is the infinite backyard. Let's dissect the physics of this orbital inversion because it's fascinating. The first point is power. The text claims, quote, solar energy is abundant and essentially free once the panels are deployed.
Think about the physics of solar radiance on the surface of the Earth. Before a single photon hits a solar panel in Nevada, it has to punch through the Earth's atmosphere.
Right, which scatters and absorbs a massive percentage of the energy.
And then you have weather systems, cloud cover, dust, and of course the fundamental reality of the day-night cycle. A terrestrial solar farm only generates peak power for a few hours a day.
But in low Earth orbit.
Depending on the specific inclination and altitude, a satellite can experience near-constant, unfiltered, perfectly direct sunlight. There is no atmospheric attenuation.
No weather.
No weather. The energy density hitting those photovoltaic arrays is relentless and vastly superior to anything on the surface.
Do you deploy the panels and you have a baseload power source that never shuts off? But that immediately raises a massive red flag for me.
Oh, the heat?
Yes. If we have unfiltered, relentless solar radiation hitting these server modules, and the GPUs themselves are generating gigawatts of internal heat, wouldn't the whole thing just turn into an orbital oven? Like, how do you cool a server farm in a place with no air and no water?
It sounds impossible.
Yeah.
But the author points to radiative cooling as a natural heat sink in the vacuum of space.
Okay, walk us through that.
This is where the engineering paradigm completely shifts. You have to abandon the terrestrial concept of cooling. On Earth, cooling relies on conduction and convection. You physically transfer the heat from the hot silicon into a fluid, like chilled air or liquid water.
And then you move that fluid away.
Right. You cannot do that in orbit because space is a vacuum. There's no ambient fluid to absorb the heat.
So where does the thermal energy go? Does it just sit there?
It leaves via thermal radiation, which is governed by the Stefan Boltzmann law.
Okay,
Any object with a temperature above absolute zero emits electromagnetic radiation. In the vacuum of space, an orbital data center would utilize massive radiator fin structures made of highly conductive materials that are specifically oriented away from the sun.
And shielded from the Earth's reflection, I assume.
Yes, shielded from the infrared albedo of the Earth itself. These fins simply radiate the excess thermal energy away as infrared light into the infinite expanse of the cosmos.
Wow.
The background temperature of the universe is roughly 3 Kelvin. It is an infinite, boundless thermal reservoir.
So it's not a box with fans. It's a massive metallic feather with gigantic fins spread out into the dark, constantly bleeding infrared light into the void.
That's a beautiful way to picture it.
You aren't boiling millions of gallons of drinking water. You are just letting the heat bleed out into the background of the universe. The capacity for cooling isn't just large, it is theoretically limitless.
Now, the engineering challenge is significant. You need massive surface areas for those radiators.
Right, they have to be huge.
But the fundamental physics means the ultimate heat sink for exascale computing isn't an ocean or an aquifer. It is space itself.
Okay, so the power is continuous and unfiltered, and the cooling relies on the infinite thermal reservoir of the universe. But here is the most counterintuitive claim in the entire piece, at least to me.
The data transfer.
Yes. The author states that constellations of satellites linked by laser interlinks will provide near light-speed data transfer, slashing global latency compared to undersea cables. My instinct is if the servers are hundreds of miles up in the sky, it must take longer for the data to reach my phone.
It feels completely counterintuitive until you look at the physical properties of the mediums transmitting the data. The global internet currently relies almost entirely on thousands of miles of fiber optic cables resting on the ocean floor.
Right.
Fiber optics transmit data using light, but they send that light through silica glass.
And the speed of light is not a constant when it's passing through a physical medium.
Exactly. The speed of light in a perfect vacuum is roughly 300,000 kilometers per second. But the refractive index of the silica glass used in undersea cables is around 1.47
So it slows it down?
by nearly 35%. It's moving at roughly 200,000 kilometers per second.
Not to mention the fact that undersea cables don't run in perfect straight lines.
No, they have to follow the topography of the ocean floor,
Hmm.
hit specific coastal landing stations, and route through massive terrestrial switching centers before they ever reach a local ISP.
It's a torturous, physically slower path.
Right. And the orbital architecture the author is proposing bypasses that entirely. You beam the data from a ground station up to a satellite in low Earth orbit using radio frequencies or lasers.
Okay.
Once the data is in the constellation, those satellites communicate with each other using optical laser interlinks point to point across the vacuum of space.
Because there is no atmospheric or physical medium between them.
Yes. The light carrying the data is traveling at its absolute maximum physical limit, a true 300,000 kilometers per second.
That is wild. So a financial institution in London executing a high-frequency algorithmic trade with a market in Singapore would actually experience significantly lower latency bouncing the signal off an orbital server farm than routing it through physical fiber buried beneath the Indian Ocean.
Mathematically, yes. For global, highly distributed workloads, the vacuum of space isn't just a viable alternative. It is a physically superior medium for data transmission.
Okay, so the physics of the LEO inversion are elegant, but we've understood blackbody radiation and the speed of light in a vacuum for over a century. Why is this author arguing that this is the inevitable next step right now? Because the catalyst he points to is the plummeting cost of launch, driven entirely by reusable rockets.
Right. For the first 60 years of the space age, the economic barrier to entry was insurmountable for large-scale industrialization because the launch architecture was entirely expendable.
You built it and threw it away.
You spent tens of millions of dollars building a highly complex, precision-engineered orbital launch vehicle. You flew it exactly once, and then you dropped it into the ocean.
The economic equivalent would be throwing away a Boeing 747 after a single flight from New York to London.
Exactly. At that cost paradigm, the only things worth putting in orbit were multi-billion-dollar spy satellites or bespoke scientific instruments.
But the text notes that we have decisively crossed an inflection point. Reusability has shattered that cost structure. We are no longer throwing the airplanes away. We are landing the boosters, refurbishing them in days, and flying them again.
Once the cost per kilogram to low Earth orbit drops below a certain mathematical threshold, the economic advantages of free solar power and free vacuum cooling begin to dramatically outweigh the initial cost of launching the server hardware.
It becomes a no-brainer.
The author believes the arrival of fully reusable super heavy lift vehicles is the exact catalyst that moves orbital data centers from science fiction to an urgent economic imperative.
Which brings us to the operational reality. We have the physics and the launch economics are aligning. But how do you actually build an AWS-in-orbit?
It sounds like sci-fi.
Right. But the author anchors his argument in a very specific operational precedent, which is Starlink. He argues that if one network proved millions of terminals on Earth can be served reliably from orbit, that exact same engineering discipline can be applied to compute clusters.
Starlink is the crucial proof of concept here. Before massive constellations, the consensus was that managing thousands of satellites in low Earth orbit, orchestrating seamless handoffs as they streak across the sky at 17,000 miles per hour and avoiding collisions,
Would be an absolute nightmare.
a software and operational nightmare. But the software architecture has been proven. The phased array antennas work. The autonomous collision avoidance algorithms work.
The author is simply saying, stop looking at those satellites as mere communication relays and start looking at them as the backbone for flying server racks. Let's visualize the hardware he's proposing, though. The text explicitly calls for modular, radiation-hardened servers because running an exascale AI cluster is fundamentally different from bouncing radio waves. You are exposing incredibly dense, cutting-edge 3-nanometer transistors to raw cosmic radiation.
Beyond the protection of the Earth's thick atmosphere and the bulk of its magnetosphere, silicon is constantly bombarded by high-energy particles, galactic cosmic rays, and solar proton events.
Right, and if one hits a chip.
If a high-energy particle strikes a standard terrestrial microchip, it can deposit enough charge to literally flip a bit in the memory from a 1 to a 0.
Oh!
This is known as a single-event upset. In a neural network processing billions of parameters, a cascade of bit flips corrupts the entire output.
And you can't just wrap a server rack in a foot of lead because the mass penalty for launching it would destroy the economics. So how do you harden it?
It requires a multi-layered approach. Physically, you manufacture the chips differently. perhaps using silicon on insulator technology, which isolates the transistors and makes them far less susceptible to ambient charge.
Okay.
Architecturally, you use triple modular redundancy.
Which is what?
You have 3 separate processors running the exact same calculations simultaneously. If a cosmic ray flips a bit in processor A, processors B and C will recognize the error, outvote processor A, and output the correct result.
That's brilliant.
And the author's use of the word modular is also key here. You aren't launching a massive monolithic supercomputer. You are launching standardized, Lego-like compute blocks.
Because things will break. The radiation will eventually degrade the silicon, and thermal cycling will stress the materials. And since you cannot economically send IT technicians in pressurized spacesuits to swap out a bad GPU...
Right, no space mechanics.
Exactly. The text emphasizes that these modules must be assembled and serviced by robotic spacecraft.
This envisions an entirely autonomous orbital ecosystem. When a compute module degrades, an autonomous or teleoperated servicing drone, essentially a highly specialized space tug with robotic arms, navigates to the constellation.
It just flies over to it.
Physically undocks the degraded server blade, slots in a newly launched replacement, and deorbits the old hardware to safely burn up in the atmosphere. The entire maintenance cycle happens without a human being within hundreds of miles.
From the perspective of the end user, this is the ultimate abstraction of hardware. If I'm a machine learning researcher at a major AI lab, the text suggests my workflow doesn't change at all.
Not one bit.
Hyperscalers won't care where the physical servers are located. I simply log into a portal, write my code, and rent capacity by the petaflop. My API calls bounce off a ground station, beam up to an orbital compute cluster, the model trains in the vacuum of space, and the weights are beamed back down to my laptop.
The physical infrastructure becomes entirely invisible to you. The AI labs are completely emancipated from terrestrial utility monopolies. They don't have to lobby a city council for zoning permits, or negotiate water rights with an agricultural district, or wait 5 years for a high-voltage substation upgrade.
They simply scale their operations in the limitless domain of Ilio.
Limitless.
But building that limitless domain is where the author's vision stops sounding like a standard corporate pitch and starts sounding like the blueprint for a Type 1 civilization.
Oh, absolutely.
The text makes a staggering assessment of the required scale. It states that to achieve this, humanity needs at least 10 companies operating at SpaceX's current level of ambition and execution.
This is a vital point in his argument. Currently, SpaceX is a singularity in the aerospace industry. It launches more mass to orbit on an annual basis than the rest of the entire planet, all other nations and companies combined.
Which is a crazy stat.
It really is. And the author is looking at that incredible cadence and arguing that it is vastly insufficient. To build exascale compute constellations, we don't just need one visionary company. We need an entire heavy industry ecosystem operating at that exact same relentless pace.
We need a tenfold increase in global launch capacity just to establish the baseline.
Just for the baseline, yes.
And it's not just about rockets. The text outlines a massive orbital supply chain that includes orbital factories, in-space assembly, propellant depots, and maintenance fleets. Let's dig into the necessity of orbital factories. If we have reusable rockets, why can't we just mass manufacture the server racks and massive radiator panels in automated factories on Earth and then just launch them?
Because of the launch bottleneck, specifically the physical dimensions of the rocket's payload fairing. Reusable rockets drastically reduce the cost per kilogram, but you are still constrained by the volume of the nose cone.
Right, you can only fit so much inside.
The physics of exascale compute require massive structural elements. Solar arrays the size of several football fields, and gigantic, sprawling radiator fins to dissipate the gigawatts of heat. If you build those on Earth, you have to engineer incredibly complex, origami-like folding mechanisms to cram them inside a rocket fairing.
And every hinge, every motor, every deployment mechanism is dead weight that reduces your payload capacity.
And a single point of failure. If a solar array gets stuck halfway through unfolding, a billion-dollar module is just dead in space.
Which violates the Tsiolkovsky rocket equation, right?
Brutally. It punishes every single ounce of dead weight. The author's solution is radical, but mathematically sound. Do not launch deployed structures. Launch raw materials.
Okay, so you just send up dense spools of carbon fiber, aluminum, and silicon.
Right. Then robotic orbital factories utilize zero-gravity 3D printing and automated extrusion to manufacture the massive structural trusses, radiator fins, and solar backings directly in space.
Which is amazing because zero-gravity manufacturing completely changes the limits of structural engineering. On Earth, You have to build a solar array strong enough to survive its own immense weight under 1G, plus the violent acoustic and vibrational environment of a rocket launch.
It has to be incredibly sturdy.
But if you print it in orbit, it only has to be strong enough to survive the microstresses of orbital station keeping. You can build structures that are incredibly massive, yet incredibly fragile and lightweight by terrestrial standards.
And once the orbital factory extrudes these massive components, you utilize in-space assembly. Swarms of autonomous robotic arms and tugs weld the trusses together, slot the delicate silicon compute modules into the massive radiator frameworks, and integrate the whole system.
But those robotic tugs and assembly drones need to move around. They need fuel to change orbits, match velocities, and dock, which is why the author explicitly lists propellant depots as a necessary piece of the supply chain.
You cannot build an orbital economy if every space tug has to return to Earth to refuel. It is energetically prohibitive.
You lose all your efficiency.
Exactly. The vision requires launching massive tanks of cryogenic propellants, liquid oxygen and liquid methane, and parking them in stable orbits. These depots act as the gas stations of the orbital compute economy.
But managing cryogenic fluids in a vacuum is incredibly difficult, isn't it?
Oh yes. You need advanced sun shields to prevent the fuel from boiling off due to solar radiation.
I mean, this entire section reads less like a proposal for a new data center and more like the foundational infrastructure for colonizing the solar system. We are talking about establishing a permanent, heavy industrial presence in the vacuum of space, complete with factories, gas stations, and autonomous maintenance fleets.
It's civilization-level infrastructure.
Which begs a massive, unavoidable question. Where does the talent and the astronomical capital come from to build this? We are talking about trillions of dollars and massive armies of the world's most brilliant minds.
And this is where the author's macroeconomic analysis brilliantly anchors the science fiction in current geopolitical realities. He doesn't just pose an impossible engineering megaproject, he identifies the specific pools of talent and capital currently available on the planet to execute it.
Okay, so who builds it?
He points to a very specific geopolitical marriage. First, for the talent, he identifies India.
The text is incredibly specific about India's role. It states that India produces hundreds of thousands of world-class engineers every year, software architects, aerospace specialists, hardware designers. He notes that these are the systemic thinkers who have already powered Silicon Valley and who built the Indian space research organizations, ISRO's, highly successful launch vehicles.
India possesses an undeniable world-leading demographic dividend in technical education. It is an engine of human capital. Furthermore, ISRO has cultivated a unique culture of frugal, highly efficient aerospace engineering. They have successfully executed complex interplanetary missions, like the Mars Orbiter mission, and sophisticated lunar landings at a fraction of the cost of legacy Western space agencies.
Because they work differently.
They utilize concurrent engineering and leverage a vast domestic industrial base to iterate rapidly. The author sees this proven, scalable human capital as the necessary workforce to design the radiation-hardened silica, write the autonomous docking algorithms, and mass manufacture the orbital server modules.
So you have the aerospace engineering base to build the physical infrastructure and the software engineering base to architect the exascale neural networks that will run on it. But, I mean, human capital alone cannot build heavy-lift rockets or orbital propellant depots. That requires immense, patient, high-risk capital.
Trillions of dollars.
Trillions of upfront investment before a single petaflop of compute is sold. And the author points directly to the Gulf sovereign wealth funds to supply it.
The text astutely observes a massive macroeconomic shift currently underway. The sovereign wealth funds of nations like Saudi Arabia, the UAE, and Qatar are sitting on trillions of dollars of investable capital, historically generated by the global hydrocarbon trade.
Oil money.
Yes. But these nations are acutely aware of the impending post-oil reality. They are actively seeking to diversify their economies and transition from pure energy plays into technology.
But the author is explicitly saying that simply acting as limited partners in Western venture capital funds or buying minority stakes in existing AI software startups is vastly insufficient.
Too small.
The scale of deployment required for orbital infrastructure demands a step change in boldness.
He is proposing a structural synthesis. You pair the unparalleled engineering depth and demographic dividend of India with the immense, highly liquid, and structurally patient capital of the Gulf. The author calls this the perfect marriage of brain power and balance sheet firepower.
The text suggests formalizing this alliance through joint ventures, special economic zones dedicated to space tech manufacturing, and specialized orbital investment vehicles designed to turn idle hydrocarbon capital into the physical backbone of the 21st century compute economy.
This is a blueprint for a profound realignment of global technological supremacy. The author is outlining a new axis of innovation that explicitly bypasses the traditional dominance of the West in both cloud computing and aerospace engineering.
He is arguing that the nations that build the orbital infrastructure will dictate the terms of the AI age.
Completely.
This feels incredibly historical to me. It perfectly mirrors the dynamics of the 16th century. During the Age of Exploration, you had master shipbuilders, cartographers, and navigators who possessed the technical knowledge to cross the oceans, the talent,
Right.
but they couldn't leave port until they secured massive, highly speculative funding from royal treasuries, the capital. When the navigational talent married the immense capital of the crown, they built armadas that fundamentally shifted the center of the global economy.
That's a stunningly apt historical parallel.
The author is drawing the exact same blueprint. The heavy-lift rockets and orbital factories are the new armadas, low Earth orbit is the new frontier, and exascale AI compute capacity is the most valuable commodity in human history.
And it leads directly to the most critical question of the entire text. If the physics are sound, the launch economics are viable, and the talent and capital already exist in these specific regions, why isn't it happening right now?
Right. Why aren't we seeing ground broken on massive orbital manufacturing facilities in these special economic zones today?
That brings us to the author's most piercing and controversial critique. He argues that the bottleneck is not technological and it is not financial.
Say psychological.
It is entirely psychological and cultural. The missing piece, according to the text, is a fundamental lack of audacity among current decision makers.
He dissects the psychology of incrementalism that dominates modern leadership. He observes that decision-makers operate with the caution of yesterday's empires. They are heavily incentivized to pursue incremental gains, rely on risk-averse procurement cycles, and operate entirely within short political horizons.
The mismatch is glaring. In modern corporate and political structures, leaders are judged on quarterly earnings reports or 2 to 4 year election cycles.
But building an orbital megastructure requires committing trillions of dollars to a vision that might take 15 or 20 years to yield a profitable return.
The author is arguing that short-termism makes civilizational scale engineering impossible.
But he goes much deeper than just critiquing generic corporate bureaucracy, right? He provides a profound historical context for this lack of audacity, specifically aimed at the very regions he identified as possessing the talent and the treasure.
Yes. The text contains a crucial line. Historical patterns of external rule and colonial administration left a cultural residue of deference and incrementalism.
That is a staggering sociological point. He is arguing that in regions that experienced centuries of external imperial rule, the administrative and bureaucratic systems left behind were fundamentally designed by the colonizers to do three things: maintain control, mitigate risk, and extract resources incrementally.
They were explicitly not designed to foster a bold, relentless, first principles drive.
The author suggests this colonial residue acts as a massive psychological overhang. It creates a culture where the default leadership posture is bureaucratic caution rather than visionary pioneering.
Leaders are subconsciously trained to defer to established legacy systems, which are almost always Western systems, rather than trusting their own talent to architect entirely new paradigms from scratch.
It leads to an environment heavily reliant on cost-plus contracting and administrative consensus.
Rather than the hardware-rich, fail-fast, iterative engineering that drives true aerospace breakthroughs.
The result is an ambition that feels strangely low for nations that possess such an overwhelming abundance of potential. The author is throwing down a gauntlet here. He is saying that to colonize orbit and build the future, these nations must aggressively shed the administrative caution of the past.
They must stop asking for permission from the legacy systems.
The text explicitly frames ambition not as an inherent static trait, but as an active practice. Quote, "Vision is a choice. Ambition is a muscle that strengthens with use."
This is the ultimate call to action in the text. The nations that choose to actively flex that muscle by heavily subsidizing reusable launch vehicles, constructing massive in-space manufacturing prototypes, and creating aggressive public-private partnerships for compute constellations,
are the ones that will capture the astronomical economic upside of the AI age.
And the warning for those who fail to flex that muscle is incredibly stark. The author draws a brutal comparison to the recent past of the tech industry.
Oh, the cloud computing comparison?
Yes. 10 years ago, companies that hesitated to build their own internal cloud infrastructure ultimately capitulated and were relegated to renting server capacity from bolder players like Amazon or Microsoft, fundamentally losing control over their underlying technical foundation.
The text argues that nations that hesitate now will suffer the exact same fate on a geopolitical level. They will end up perpetually renting their foundational AI brainpower from whoever had the audacity to build the orbital compute platforms.
In an age where artificial intelligence will govern everything from national security to global financial markets to energy distribution, compute is not just another commodity. It is the ultimate strategic resource of the 21st century.
If a nation does not control the physical infrastructure upon which its AI operates, it has fundamentally surrendered its sovereignty. It's a winner-take-all scenario playing out in the vacuum of space. Which brings us to the end of this truly epic journey. I mean, we started deep in the physical exhaustion of Earth's data centers, the strained, aging electrical grids, the millions of gallons of evaporating water, the vicious competition for land.
We saw the undeniable reality that the boundless appetite of AI cannot be contained within the thermodynamic limits of the biosphere.
Right. And we followed the author's mathematical proof out of the atmosphere, discovering that the harsh vacuum of low Earth orbit actually inverts all of Earth's bottlenecks.
It provides a relentless, unfiltered baseload of solar energy, an infinite thermal reservoir for radiative cooling.
And a vacuum medium that allows laser interlinks to transmit data significantly faster than terrestrial fiber optics. We saw how the advent of reusable rockets makes the launch economics viable and how the operational success of Starlink proves the constellation model.
We stared at the terrifying, awe-inspiring scale of the industrial mobilization required. 10 companies operating with the sheer force of SpaceX, constructing orbital factories, in-space assembly nodes, and robotic maintenance fleets.
We analyzed the proposed geopolitical mega-alliance, merging the vast, proven engineering talent of India with the trillions in sovereign wealth from the Gulf, requiring only that they shed the psychological residue of history and embrace the audacity of first principles engineering.
My final takeaway, looking at how the author weaves ancient prophecies of abundance with the hard physics of exascale compute, is his closing sentiment regarding the nature of space exploration itself.
What's that?
Well, for over half a century, space was treated as a domain for pure science, national prestige, or, planting flags. What this text definitively argues is that the era of space as a prestige project is over. Space is now simply the logical, necessary, and inevitable industrial extension of the data center.
It's just infrastructure now.
Exactly. The compute revolution is arriving faster than terrestrial infrastructure can handle. As the author puts it, we either build the infrastructure to support it in orbit, or we watch the future happen without us. The math, the physics, and the economics all point directly to the stars. It is now purely a matter of who possesses the collective civilizational will to follow it.
The math points up that the consequences will all be felt down here. Now, earlier in the deep dive, we briefly touched on a critical term the author used, data sovereignty. And as we wrap up, I want to leave you, the listener, with a profound logistical and legal question inspired by the text. If the author's vision comes to pass, and the entire world's AI brain, the systems managing global equity markets, controlling autonomous supply chains, and holding our most intimate biometric and healthcare data is physically located in thousands of flying server racks in orbit, who actually governs it?
It's a huge question.
The Outer Space Treaty of 1967 states that space is the province of all mankind and is not subject to national appropriation. But if a massive multinational constellation holding critical financial data is subjected to a cyber attack, or worse, a kinetic strike from rogue space debris or an anti-satellite weapon, who has jurisdiction in the vacuum of space? If the physical cloud is entirely untethered from the Earth, operated by a new, unprecedented coalition of sovereign wealth and international talent, what earthly authority can hold it accountable? Think about the sheer vulnerability and the unprecedented shift in power that implies. Think about that the next time you use an AI agent on your phone to summarize an email or check a stock price. The intelligence answering you might be raining down from a robotic, sun-drenched server farm moving at 17,000 miles per hour, completely beyond the physical reach of any law on Earth.